Good morning, everyone. It's a pleasure having you here with us today. My name is Jordan Hales, and I'm an Energy Systems Engineering intern on the supply side for the Caribbean Center for Renewable Energy and Energy Efficiency, or the CARICOM for short. Welcome to the IRRP series of capacity building sessions brought to you by the CARICOM in partnership with the Climate Resilient and Sustainable Energy Supply in the Caribbean Project, CLIRES, funded by the German Corporation for International Cooperation, GIZ, and the German government in partnership with the European Union. Planning for the future of the electricity sector requires an appreciation of the technical issues arising from grid expansion with renewable energy integration, as well as responding to the demand side changes. These sessions are designed to address critical elements of the Integrated Resource and Resilience Planning, IRRP process. As the CARICOM works with stakeholders towards delivering IRRPs for several Caribbean countries, our aim is to build institutional capacity for energy planning across the region. In today's capacity building session, we will explore solar integration. Just one housekeeping matter. You have the option of typing and submitting your questions using the Q&A chat throughout the session, and we'll pause periodically just so that we can address the questions. Now today, our capacity building will be led by Dr. Randy Kunkun, who is a lecturer at the Department of Physics at the University of the West Indies Mona campus. We will also have Mr. David Barrett of NBAR Consulting in Jamaica, and Mr. Lincoln Small, who's from the Jamaica Public Service Company Limited. We look forward to an interactive and productive session, and I will now hand over to Mr. David Barrett. Thank you.
Good morning. Thanks for this opportunity to be a part of this event. Indeed, I think it's a very important one and a very timely one. Just apologize, just give me a second. I'm going to Are you now able to see my screen? Are you seeing my screen?
Yes, David, just switch to presenter mode.
Yes, okay. All right, great. You're able to see that.
Yes, you may go ahead.
Yeah, we can see.
Excellent. So, just want to start by highlighting that in the Caribbean, we have set fairly moderate targets, 47% of renewables for power by 2027, and that's through CARICOM. And also we intend to reduce the amount of carbon emissions by 36% by 2027. The good thing is that all those things align very well with the Sustainable Development Goals. And the three that would apply in particular would be one, affordable and clean energy, which I think many of us would already be exposed to. It's the intention to ensure that there is good access and affordability and reliability of sustainable, modern, and of course, clean energy options. Then there's Sustainable Development Goal number 9, which talks about infrastructure, building resilient infrastructure, which a lot of this presentation and today's activities will be about. And then there's a climate action, ensuring that we have a green outcome from all that we do, and we're able to be a part of reducing the impacts of climate change. So when we look at the CARICOM renewable energy targets, what we see, again, as I mentioned, are a range of policy targets, the highest ones being for Dominica, St. Kitts, and Barbados. But then other countries have more moderate targets, Belize with 56%, 85%, and others coming way down to 20%, 28%. Within that band are specific renewable energy targets, primarily hydro, biomass, solar, and wind. And countries of the Eastern Caribbean have added geothermal to their ambitions. But in terms of today's focus being solar, the amount of solar that has been installed, as you can see, countries like Jamaica has 67 megawatts. You have Barbados with 30, and the other countries have moderate inclusions as it relates to their own demand and their grid size. And it's important to note that for these numbers that you're seeing, that the systems are grid interactive, they're standalone systems, some of them are utility, you have distributed units. And in terms of the percentage of the energy mix within these countries, it ranges from very small numbers, Trinidad with 0.005, to about 56% of their energy mix. When we look at how does a state move the ambitions towards the targets which we mentioned earlier, a lot of times, and especially in the earliest points, you have to use some amount of incentives because fossil fuels have been established. And so when we look at the renewable energy type incentives for 2020, we see a range of initiatives. Tax credits are one, and not many countries within the CARICOM have used tax credits. We have feed-in tariffs, which established rates for which the renewables can be fed. That has not been widely used, but a number of countries have. Barbados has, St. Vincent. Net metering and the net billing are an increase or an improvement on that. And as you can see, that there are different responses from different countries. They have included net metering or net billing. Net billing basically means that you receive power from the utility. You have to be a client, but the rate that you get back for the power that you deliver is much less than what you are charged. Net metering is one-to-one. Same amount the utility charges you, the same value that you receive. Tax reductions and exemptions, though, is a very big opportunity that has been used to encourage renewables, and particularly solar, and the interconnection standards are in place in a number of the countries. So CARICOM also recognizing there's a climate change dimension to its mitigation activities, its energy ambitions, acknowledges that there's a benefit for using renewables for mitigation and environmental adaptation. And also it facilitates the countries moving towards greener economies and low carbon economies. When we look at the different initiatives under the National Determined Contributions, NDCs, the mitigation actions, particularly in the energy sector, shows that renewable energy added to the grids is the most progressive of the methodologies or the mechanisms used. But then also developing clean energy policies and strategies has also moved us along the way. And then you have energy efficiency, followed by greenhouse gas monitoring and tracking systems. And then you have grid efficiency improvements, which are added to that. So just want to close by noting that national renewable energy ambitions are fairly high, some countries lower than others, but to bear in mind that there is a meaningful renewable energy gap that has to be filled. A number of countries have not as yet achieved their full potential in the full band of renewables. And the significant potential for more grid interactive solar is there in order to meet the policy ambitions. So certainly policies can do much more, and the measures to incentivize renewables can be advanced, and renewables certainly is, and solar is one of the most progressive options for moving us along the climate change mitigation and sustainable grid expansion path. So thank you for this, your attention in this section, and I hand over.
Currently not seeing any questions in the chat.
Hi, good morning. Okay, so I'd like to say thank you again for this opportunity to be here and deliver this solar photovoltaic training session. I'll be delivering a couple of topics here that might be a bit, new, might be a bit familiar to some of us. Just one logistic point I like to make: as you move forward for your PowerPoints, feel free to use your phones or whatever to scan the QR codes as you go along. It's a great point of interest. You can access the available data and presentations and diagrams that you will be seeing as we move along. So just to give you a guide on what's for today's session, we've just had the overview of solar PV in the Caribbean. I'll be giving you a very short introduction into photovoltaic systems, and then we dive into the system design, distributed generation, and the utility scale, maybe some implications of having these intermittent renewables on board there. You'll be having very important building codes, plans, and inspections. Furthermore, David will take charge on number 4 and 5 there. And I'll be back later on with some very nice applications of how we can integrate PV systems into the grid. We'll be looking at a lot of online tools that we can use to really map these resource potential at that point. Some project financing, and finally, case study will be delivered by a GPS. So I always really like to begin with some basics, and then we move forward and we get a bit more, build on it as we go along. And we always need to ask the question, why transition to sustainable forms of energy? Solar power, photovoltaics, this is a renewable form of energy, which we will be defining later on. But why should we transition? Why should we? We need to understand the situation that's going on there. There's some statistics in front of you over here in Jamaica. You can see the importance of reduction of your importation of fossil fuels and the effect that can have on overall future savings of your GDP given there. So all the CARICOM members, we are very much interested in having energy security at that point. Couple that now with the impacts of the climate that we've been seeing very recently. In recent times, you see the Intergovernmental Panel on Climate Change issued that very important document, SR15, and its estimations for 1.5 and nothing beyond. So we need to hit carbon neutral by mid-century or just after at that point. And what is this leading to, right? If we continue on that path, more and more carbon emissions into the atmosphere, we have much more adverse effects of this climate system. So how can we help? This is where solar power can come in, a form of renewables. And just to give the idea, the benefits that we can have at this point, right? Some of these points we will be touching on. These are certain points of mention that we should be talking about: carbon dioxide reduction, levelized cost of energy or electricity as it's termed in terms of dollars per kilowatt hours, something that's very important to us in the Caribbean because we have an average retail rate of 35 US cents per kilowatt hours. And this varies from island to island as it goes about job creation and grid stability. Grid stability is a very important aspect that we'll be talking about, how it can have implications, and then how can we resolve those implications at the same time, right? So when you think about solar power, when you think about solar photovoltaics, right, we can get as beautiful as the scenery over there in the Maldives, bottom right of the screen, we can get as integrated and comprehensive over at the UAE. At that point, that was scheduled over in 2018. That's been going to be updated there, right? You can see the fascinations. So the versatility of solar photovoltaics, it does not have to take on always large solar farms. It is very flexible. It can be integrated within the households, which is very important, and that's going to help with that grid stability point that we're going to be talking about later on. So is solar power a renewable source of energy? I just like to pose these questions for you, the audience, to excite your minds on this. Of course, it is. It's a renewable form. It is replenishable over human time scale. We have those ideas, and so solar photovoltaics. We're going to define that as for electricity generation. Right, as we move along, we will not be looking at the direct use as it is here. And it's a few more basics as we go along. We have the idea. Solar radiation, or irradiance as it is, right, is one of the most important parameters when we're looking at resource assessment of our site locations and stuff. And we know the effect of latitude as it is. In the Caribbean here, in CARICOM member states, we're close to the equator. We have vast abundance of this solar radiation. And let's take, for example, a map of Jamaica here in terms of the global horizontal irradiance. That takes into account a couple more technical terms that you can always look into it. The direct normal and diffuse horizontal radiation is a combination of those parameters. Feel free to check out the QR code, and you can also go on and access these maps around the world on Solar GIS and have an understanding of this PV potential as we go along. And this is very important for site selection, right? Because that's a big part of what we're going to be talking about. So I'm wrapping up the first part there, and I'm going to start going into the photovoltaic system design, and we're building on these ideas now for distributed generation and utility scale. So we're going to be introducing certain components. What are the building blocks as we move forward? So let's get started once more. So when we think solar photovoltaics, you need to understand what type of material that you're using, what type of module that you're going to be using. Of course, the cell by itself is the building block, the single building block as it is. And you can go, and I want you to have a look at these little diagrams that just popped up in front of you here, right? Some of us might be more in some atomic structures and stuff at that point, and we can relate to those ideas better. So we have a more rigid alignment in our monocrystallized or mono SI as it is. And of course, we know silicon, a vast abundant element on the planets, and it's one of those very versatile ones at the same time. Then we have our poly SI. All right, I want you to have an understanding and also an observation on the material design and have a look on it. And then we have our last one here, the amorphous or silicon, right? Or the thin film as it's also called. And this gives a bit more versatility in which you can have these integrated into certain designs and geometries and stuff, because it's much more versatile in its structure as it is compared to the others, right? So once when we said the solar PV cell, right, is a single building block here, but how is electricity really generated? Of course, we know solar radiation gives the energy, it excites electrons, and some sort of excitation is going to cause, if we remember our days in chemistry, or just have a quick recap there. To generate the current, we just need a flow of electrons, and that's it, right? So this is the technology now with the cell itself. We term it as an N-type and a P-type. The N-type is towards the sun itself. It has an excess of electrons, and it flows into this P-type side where there's a deficit or holes, as we call them. It fills at that point, and it creates an electrical current, right? And just one more building block, one more basic point before we move on. I just want to get you the laws that govern these cells. And I want you to think about how we're going to be adding up because we will be doing energy audits later on in our system and how important it is, right? So I want you to think about what happens here in series. And I just want you to look at the poles that you're seeing, plus, negative, right? So once they go opposite, we know we're in a series arrangement. If they're in like terms, they're in parallel. So, and this is something you could try on your own if you do remember these ideas. So we're going to be adding those voltages Current remains the same for series, and we know for parallel it's the opposite. And we'll be just touching briefly on that later on. But let's get to the meat of it here now. We want to look at, firstly, say a small scale application. At the same time, some building blocks. We have the system itself here, the PV system array, right? So the PPV modules are built up. It's linked to the combiner box. And we're going to be having a look at what exactly is attributed to that combiner box. We then have to have a DC disconnect. And this is very important because we know on the left-hand side of the inverter, right? I'm just using Fronius inverter here as an example, a very well-known one in the Caribbean. Everything on the left-hand side is going to give us DC power generation from that sun as it is. And everything on the right-hand side now, the main function of that inverter is to provide your AC power. So we normally have these disconnect points as safety protocols for any engineer that's coming on site to inspect the system. It's always very important to have these break points, right? To have no live current within any portion of it. And then we have our main utility panel linked to our utility provider, and we have an optional system of having our battery bank here. And something you're probably thinking about, yes, there's something that we meshed together here is a charge controller within the inverter. I just meshed them into one. We can think about feeding DC loads on this side. And we can also think about what's the probable causes of losses within the systems and how can the system be improved, right? Because this is not a one fix system. This is a general idea. And now we're going to be building on these ideas a bit more, right? Of course, your metering system can be linked to that. And we've advanced with a bi-metering system where we can take from the electrical grid and we can feed back to the electrical grid in our points of excess. I always like to use this example. It's on the rooftop of my physics department over here at the UWI Mona. And over in this area, to that area, that's the science library. That's another system. There are 20 kW PV system that we have there. And I want you to think about it. It's nice 4 strings that we have here. All right, I'm just going to give you an idea of what you're seeing here. 1, 2, 3, 4. On your own time, you can give it a count. If you're looking back at the video, feel free to check out the QR code for more information on that there. And this is what we're talking about. This is this combiner box. It basically takes all those strings, links them on a parallel systems, gives us as a combined version, gives us a safety point where we can actually either turn on or off the system at the same time with these breakers and alignments. And then we could also always have our inverter and AC disconnect all later on at that point, right? So we just have that. And now this is the meat of it here. So I'm going to take a quick time check. I'm going to keep moving forward. Let's have a quick energy audit exercise here, right? You can also do this on your own time and check back. So what we're going to have here is that it's very important to look at the load demands of a system. And that gives us an idea on how we can size the actual system. Now, in a small scale application, it's extremely important. If you're in a large scale, like content solar, as we're going to be looking at very soon, we can do the opposite. We have LAN availability. Let's check how much power amounts, power capacity that we can get. So let's have a quick look at this. We have descriptions of the load demands, the quantities, the power ratings, and the operating times. Always follow the units. That's how you can determine what's going to happen there. You can always do some quick multiplication on your own time. Let's accept this is what we're going to be getting in the energy consumption for the AC system, right? I've labeled, stated here that this one is going to be the AC. Let's have this to be our DC loads of our system over here. Much smaller, much less loads, right? We're seeing here. You can always do a quick addition and sum these numbers up and have the inverter efficiency as 0.95. Let's take this table, which may look a bit new, and let's get it into a system component diagram now to make sense. Our PV system there, we want to determine how much is actually coming from that system as it is. We know what our AC load demand is. We started off at 6320. Let's look at what the battery inverter efficiency was at 95%. So what is going to be on the left-hand side of the inverter? If we're going to add some basic maths is going to give us that answer there quickly. But is that the true amount that is coming from our PV system on the roof mounted? That will be no, because let's think about it. We have DC loads that we can feed everything that comes before the inverter. And that's what's going to be happening here. That 144 that we extracted off, And now we know once we add those two, everything else goes up again. And of course, that 95% can be due to losses in the inverter. The idle function of the inverter takes up some sort of a power at that point. And I really wanted to have this slide to visualize how you can move from an energy audit situation and understand where those numbers lies, where those numbers actually located in your overall system. I'm coming up very soon here now, and let's see content solar, right? Some general project descriptions. So we have a large scale appreciation of what's going on. Launched over there in 2018, right? Commercial operations, 20 MWs, a large system, right? Over 91,000 solar panels, 160 acres. And of course, this is very important now because this is where the discussion is going to launch into grid 33 kV to 138 kV. We're going to be talking about high voltage transmission lines very soon, right? At that point. So let's have a quick idea here again. So we have an idea where content solar is located right at this point. Now thinking about it, remember those solar GIS maps I introduced to you very early on? Let's think about it. There's a quick analysis. We can use the resource assessment to look for locations at that point, but is that the only tool that we're going to be using to determine site location? If it was that easy, it would have been done all the time, but definitely not that simple. We're going to be investigating a lot more things, especially to the grid. I'm just using, since we have JPS reps here today, I'm just going to be utilizing this example on grid availability to those high transmission lines. How does that play a role in our overall idea? And finally, this is something I'm going to touch on because JPS is definitely going to be pulling heavy on this now. Implications. Let's sit back for a second. Variable renewable energies, such as solar and wind in the Caribbean, which are dominant forms. In today's sessions, we're going to be talking about solar. It is an intermittent source of power. So with that intermittent source of power, let's think about it, right? The availability of power production throughout the day is going to be 24/7. Even throughout the daytime, it isn't going to be a constant power supply. There are going to be fluctuations of that. And if the grid is connected to such a large system, say a 20 MW, such as Paradise Park that came on a little further on, right? That's at maximum power potential there, right? There needs to be some way of spinning reserves or backup in terms of energy storage to stabilize that power, those power fluctuations, right? This is one of those papers that we investigated. My team over here investigated those frequency control issues that can occur. So through the further integration of solar power into the national electrical grid, JPS has experienced power quality and grid stability issues with the levels of RE. It doesn't mean that the RE is a negative aspect. It is a good aspect. It brings that aspect to us, but you still need to put things in place to ensure that you're integrating a certain amount that the grid can handle. And obviously this talk will be, will be expanded by our JPS reps. So low operating frequencies occasionally resulted in generators operating outside design operating limits. And for those who like graphs, let's quickly look at this. We can see fluctuations throughout the day for power production. That's one. We have an idea it's not a smooth flow. What does that do for our systems? Have a look at this. The frequency range for our generations is 50 plus or minus 0.5 hertz. Once you go outside that region, it's a sign of trouble. It's a sign that it can cause problems in those frequency regulations. And you can see there are some instances where this can occur. And as a short period of time as that is, it definitely has an impact on the systems, right? And this is where JPS came in. This is where they introduced the hybrid energy system for the Caribbean, first of its kind in the Caribbean, very important. It's a flywheel and condenserized lithium-ion batteries. Why do we need energy storage? You have the answer. It's extremely important. It goes hand in hand with renewable energy integrations. Some project specifics are given to you right in front of you there, right? 24.5 megawatts facility. And what else can aid in the electrical grid? Let's think about this. Let's think about this question here while I transition over to my next speaker. I'll have that stewing for you at this point. All right, and I'll hand over now at this point. Thank you.
Thanks, Randy. I'm not sure if there are any questions for Randy.
Currently have one question. It says, you've mentioned a few parameters to consider for site selection. Which is most important and why?
Okay, so what I will do is just quickly mention that the solar irradiance is a very important aspect, but we will be exploring many more later on. The list of importance, that's a bit difficult to say because there's land permits, there's heritage sites, land availability and stuff. All those need to be taken into consideration, and there are many permits that needs to go in place. But from a resource assessment, solar irradiance and the grid network, those are prime to get the project up and running for construction and other site selection tools. The other aspects, they do come in later on. They definitely.
Okay, thanks. No more questions so far. Mr. Barrett.
Great. So, in the mix of everything that has been said, we need to ensure that things are installed properly and they operate the way that they are designed to operate and the way they should operate. And so we just want to look at how we establish that kind of quality. So the first thing then is, as we look at solar PV, usually there are about 2 or 3 options. There are the rooftop designs, you saw the physics department system. You have your ground mounted systems, which that's what they are. They're mounted close to the ground. But then you also have carport or pergolas designs where they're put on a raised stand, almost like a covering. For the ones that are established within the rooftop systems, there is a potential for damage to the roofs, and also there could be hazards if not installed properly. And also you have third parties who may have access to the site, and you want to make sure that third parties are not themselves exposed to unnecessary hazards and risks. And so we have to bear in mind that the currents which you experience within the solar PV systems, I mean, they can go anywhere from 500 to over 1,000 volts for the grid connected systems. And you have to bear in mind that as long as a panel is in the sun, in fact, if it's even in a lit room, it has a potential, well, it is generating, but once the circuit is closed, it will move power. And so we have to be very careful to bear these in mind. So codes are very important for ensuring that we have a preventative measure for exposure, but also for system failure. And also want to make sure that the property, the value of that capital that's invested is also protected. So solar PV system installation requires more than one type of code, unlike if you are a plumber, then there might be a plumbing code. If you're an electrician, then you may have a specific code you're following, but solar PV follows quite a few different codes. And so it's important to understand what these standards are or codes for inspections to be effectively done. So just mentioning some of the building related codes, many of the building specific codes in the Caribbean actually at this point don't really incorporate a lot of grid integrated solar PV into the design, but I know that many of them do have this in consideration. So we can move then to the international standards and use those as a proxy, or we can adopt them or we can adapt them to ensure that the building integrated PV systems are properly installed, and then inspections can happen on the back of this to make sure they're done. So, I mean, here are a few examples. The International Building Code, for example, Article 1503.2, 1507.2.9, make sure that after penetrating the roof for roof install systems, that there is proper sealing and integrity restored to the roof. The IBC again has other codes to ensure that you don't reduce the fire classification that a roof would have originally had. And more IBC codes indicate that solar systems should not compromise the structural integrity of original roof structures. So they will lay out how you space your rails, where you put your panels, and so on, to ensure that integrity is not broken. And then maybe you could look at another international code, like the International Fire Code, to see how far should we space panels if they're on a roof. You may have a wonderful long stretch of roof in a rectangular type building, but should you cover every square inch or square foot? No. So if you utilize the International Fire Code, you see there's wisdom in leaving certain spaces, but where do you leave the spaces? Well, a code like this would help you to see that you should leave maybe a 3-foot space from the apex of a A-type roof, maybe another 3 feet on the side. And typically in Jamaica and other places, you would leave a boundary of about 1 meter around your entire panel and towards the edge of the building. Then, there are other codes. National Electrical Code, for example, defines electrical safety requirements for your PV system. Sorry. We have our CARICOM Energy Efficiency Building Code. I'm hoping many of you have already gotten your copy and you have had a chance to read. And the good news is that it does include a section which looks at solar ready zone for commercial. There's also a section for residential, but that's not our focus for today. And in this particular section, it looks at things like ensuring that you manage well the mechanical live and dead loads, the conduit interconnection pathways. There are considerations for fire safety and electrical service space, and there are some other dimensions that are important to look at. When we look specifically now at some electrical codes, it's important to note that they would cover things like the guiding principles, operating procedures, to ensure that you have good, sound technical standards to govern how your grid interactive solar PV system works and how it interfaces with the overall grid and any other user of the grid. There are, in different jurisdictions, Barbados, Jamaica, Grenada, other countries, where they separate the code into specific areas of focus. So for example, the generation code focuses on that. The generation requirements for safety, proper connection, proper functionality, and so on. And the supply codes focus on that area. There are T&D codes and so on. But the main thing is that they're all a part of establishing good standards so that you can inspect at the beginning, before installation, during installation, and after, so that people are safe and the equipment is safe. In terms of the inspections with the utilities, so against the codes, then you have to do inspections before you commission and after you commission. And what are you looking for? You want to make sure that all the inputs to protect the system, to control the system, things like your fuse, your transformers, your breakers, Randy mentioned your combiner box, those breakers which can disconnect the power. You want to also make sure that the processing of that, the input information or the feeding of electrons into the system is properly installed. There's a clearance of any potential faults. We talk about anti-islanding systems. So when a grid goes down, your solar system should not continue to put power out to the grid, because of course that could be a health and safety risk for linesmen and others. And then you want to ensure that all the output systems and mechanisms, your SCADA system, your telemetry, any information that warns is functioning the way that it should, so that you can be properly warned and protected. The process would include sometimes just a physical inspection. Sometimes it includes testing of hardwired systems, sometimes just running software to make sure that they're actually functioning. And so I'm just going to touch on a couple of the specific areas of your system, whether it's ground mounted, pergolas, carports, roof mounted systems. Transformers are a big part of your utility scale systems, and you want to make sure that there's adequate installation. It's the required excitation and resistance is in place, that you have good polarity and so on. Then you have safety equipment, lightning arresters. If you looked carefully at the UWI image, you would have seen your arresters included on your combiner box. You have breakers, you have fuses, you have different components. You have your fireman switch, for example. If there was a fire, the fire brigade is not going to go up to find your combiner box and your inverter and switch out. They want to have access to a device that is easily accessible, that when they pull that switch, all your PV does not deliver power through the line, so that they can do their work safely. Because of course, in some cases, they're going to be using water, right? Grounding, very, very important for system functionality. During inspections, you want to verify that the grounding is correct, the components which should be grounded are, and that the grounding interfaces well with the grid. So grounding methods, size of grounding rods, and so on, very important in inspection procedure. You want to also make sure that system relays function well, they're well calibrated. You want to make sure you're using the right cable sizes. I have been exposed to systems which the wrong cable size was used. It was too small. The system worked for a couple of months, and then there was a fire because the cables were too small. So you want to make sure that that happens. So not because you commission a system and it turns on means that it's going to be safe. At some point, some of these flaws will come up. So you want to make sure the cables are right cables. There are DC cables coming from the DC side. There are AC cables going from the AC side, and the gauges are correct. Conduits are very important in the earlier stages of renewables, especially residential type. People were using electrical conduits on the roof, but we realized that these break down very quickly, allowing for water intrusion. We use Schedule 40 in Jamaica, which is a tough water pipe designed to be outside. Those things might seem small, but they're very important. Having your external boxes, like the one on the UWI facility, should be weather resistant. They should be able to tolerate rain over a couple of days. They should be safe in outdoors. They shouldn't break down on the light. They should keep out dust and so on. And then, of course, these grid-connected systems have a lot of software protection. They have timers and so on, and those should be functional, and some amount of software testing will be done of those along the way. Your inverters need to be the right size, and they need to deliver according to the specifications. So the parameters have to be determined and confirmed. Anti-islanding, I mentioned already. Fault indicators. If you had an issue on the DC side or the AC side or otherwise, your alarm should work. Your motorized switches should lock off the system at the relevant point. Light indicators should come up on your dash. So those are things which are often live tested at the facility to make sure they are working well. And then, of course, your systems must synchronize, because your grid connected system, your utility scale system, must not throw off the grid, as Randy pointed out earlier. So there's likely to be live measurement testing and modeling to confirm that you're complying with these things. Voltage is very important. Your system should not put out a different volts from what is on the grid that causes problems. So an inspection point. Operational metering to determine exactly how much you're generating, how much you're putting out, and then how much is being received on the utility side. Those must be tested and proven to function well. Your SCADA system, your supervisory control and data acquisition system, must liaise well or interface well with the utility to make sure that both parties are able to read and understand what is being generated and how the system is functioning. Of course, load testing should be done, and your transfer trips, that is testing all the communication software and how they upload and download information, that probably will be a live test. And then we have other dimensions which have been added to this whole inspection paradigm, and that is with the hurricanes that we have had since 2017 and others before, we realized the vulnerabilities of renewable energy systems. And Rocky Mountain Institute with the Carbon War Room have looked at how systems have succeeded or systems have failed. So just looking, you have this, so just looking at a couple of points, T-clamps are very popular for quick install of renewables, but many of them failed because either they weren't sufficiently strong or they were not bolted on the backside. And so when they wind, hurricanes don't just blow wind at one level. You get pulses, and so you literally get the panel, almost rising and falling. So when not properly bolted, those loosen up. And once you loosen one side of a panel and that panel disappears, the strength on the other side disappears. We can look at things like roof attachment failure, not properly bolted into the floor, into the roof of the building, or not properly weighted down. And there are other failures like that. In terms of those that did survive, for example, structural calculations were done to ensure that the building could take the panel. Vibration resistant modules were bolted into the rails, and ensuring that there was sufficient structural connection for the panels. So there are many systems that we have in the Caribbean, and we realize now that we're gone way beyond just building for category 3. We went to category 5 and plus. And so inspections will now consider that that's, as it were, the new floor for testing and inspections and performance. Okay. So coming from that, the Rocky Mountain Institute has its own project resilience checklist, which you can have a look at. You can go to their site and have a look at, which adds to the inspection menu, things like rooftop pre-inspection. A project by UNDP, for example, did a lot of structural integrity assessments to ensure that the roofs could take it. So it's great if your panel stays on, but what if you lose a whole roof? Then that's meaningless, right? So you want to make sure that's done. You want to make sure that you design using a specific mechanical fasteners, whether they be bolts or screws. You want to ensure that the hardware is also resilient. A lot of resilience is at the heart of CCRE's actions and activities within the Caribbean. So besides the hardware and the software, you also have some administrative compliances. You have your emergency plans that you have to put in to the utilities and to the regulators. You want to make sure that there are things like a communication plan. How do we communicate between each other, the utility and the generator? You want to ensure that the regulator inspection reports and manufacturer certification and those things are available to the utility and to the regulator. And you can look at the other administrative components. So they're also a part of the general inspection. So hopefully this places you in your workspace in a better position to prepare yourself for meeting good standards, whether they apply in law in your country or you're using the principles of international codes and standards. So thank you.
Thank you, Mr. Barrett. We have 2 questions so far. With the expected increase in intensity of hurricanes and other climate hazards, what will be the additional costs to ensure that systems may be rated for category to remain resilient in the Caribbean?
Good question. So the short answer is roughly 20% additional on the CapEx. And we'll speak about that a little bit later. And the emphasis has been primarily to add bolting, for example. So it's going to be mostly on the infrastructural side, the exposed side. So securing your panels, ensuring that the frames are rigid. So you have cross members that prevent them from collapsing. So roughly about 20% on the CapEx.
All right, thank you. Next question is, Even though we're focusing on PV systems, someone was wondering if the Caribbean is ready for net zero building solutions. And if not, why? Why you think we aren't?
All right, maybe a more difficult question. So I think many of you may be aware that UWI actually has a net zero building. It demonstrates that it can be done, it can work. It's a target we should move towards. Whether we do that or not depends a lot on the policies within entities and states to drive a net zero type building, whether building codes, for example, encourage or facilitate design design for solar within the building codes, or if it's not mandatory, and so you can add on if you wish or not. Those are things that are going to make a decision, but also there will be an additional cost initially for that. And so understanding the finances may look a little bit higher at the start, but the operational costs are much lower, enabling facilities to function sustainably and to have resilience and to have that elevated above the perhaps initial cost. Those are some decision-making points. It can be done, and policy is going to drive that significantly.
Thank you very much. I'll just check in if Dr. Kuhn has any.
Just a quickly weigh in there. Definitely, as David mentioned there, policies play a big role. I believe the building codes also, just to ensure, because a lot of our infrastructure are not up to standard, in which if in the future we want to have small scale integration of renewables into our systems, PPV, it may not be able to withstand the weight and stuff of these systems, so building codes and working hand in hand with the architecture, that goes well. Just one other point, I believe it was the previous question proposed to David. Very important again also, because this is where the climate scientists needs to be brought to the forefront also at the same time with the resource planning team. If they can forecast, as in the Caribbean, we have so many hurricanes each year, but certain years will have high intensity and frequencies. And this way they can put out additional capex, as David mentioned. He said 20% overall, but you can also have this as insurance or planning for future years, specifically if you want to term those as disaster years, or years which you have expect possible losses in the event of say category 5. So that's where the discussion needs to be brought into place, and the research is integrated at the same time with the planning for these climate scientists at the same time. That's all I'll chip in there for now.
All right, thank you. And next question is, the utility typically doesn't have visibility behind the meter to understand what is going on operationally with distributed solar. In addition, they don't always know the full extent of installed systems. What are the implications of this, and do you foresee this changing in the future? How?
All right, so a lot of what's raised has to do with the policies, the codes, and the protocols in any particular country. So I can speak for Jamaica in particular, that the utility does know what happens on the beneficiary side or the generator side, because part of the inspection protocols requires the government electrical inspectors to do that inspection, and that reports provided to the utilities. The utilities themselves also come in with their own inspection team to see the system. In the scenarios where that doesn't happen, then you are looking, the premium is human health and safety. Because if the utilities don't know if your systems can, prevent islanding, anti-islanding, if the utilities don't know if you have a disconnect switch when they are doing work on the lines and so on, then there's a possibility of health and safety issues. But also, if the utilities do not know how your system is performing, then some of those, the graph that Randy showed of these wild fluctuations for intermittent systems can significantly affect the quality of the power that is delivered to all other customers. So it's very important that the utility be included in inspections of sites, whether it's a household system or it be a utility grade system, and have the regulators inspect and confirm the status. Hence, we had gone through the matter of codes, rules, and inspections.
Thank you.
There are some cases, even in Jamaica, where the utility is not aware of when persons do not follow those channels as highlighted by David through the government inspector. And in cases like that, the utility might not be aware. One of the expectations, though, is with the proliferation of smart meters, where we'll be installing new smart meters for every customer on our grid. The hope is that even if a customer does not follow the proper protocols and install solar PV panels at their homes, using the smart meter devices, we'll be able to see bi-directional flows and probably have an indication of what is happening. And that this information from the smart grid and meters can now be fed back into our distribution management system so that we can see at least what is going on at the secondary distribution level. And that's the expectation in the future as to how we'll become more aware of situations like this.
Thanks, Lincoln. That's a good input. Thanks.
Thank you very much. All right, so we're moving on to the next presenter.
David, I believe you're continuing with the
Yes.
OHS considerations. Yeah.
Yes, sorry. All right, so I'm hoping you can see that.
Yes, we can see screen.
Great, okay. So some of the comments I made were about health and safety of persons, the beneficiaries, the generators, but also the utility. And so it's important, first of all, to just clarify two terms we use sometimes very loosely: hazards and risks. So hazards in the first place then really talks about a source or a setting, an environment that has the potential to cause harm, danger, or to create a difficult situation to individuals, whether they work in the environment or they're just a third party passing by. Now, it doesn't mean that because there is a potential source or setting or environment that there must be an event. And it doesn't even mean that you have to be able to see that. It may be foreseeable or it may be unforeseeable. But the point is that it is present, and the potential or what impact it would have then determine how you understand a risk. The risk itself then is a more statistically defined term. It's a chance, it's a probability of a person actually being harmed by being exposed to a hazard, a harmful effect. And so you have terms like, 10 in 100,000 welders may experience potential blindness. It doesn't mean that they will, but it just statistically means that there is that possibility. And so you have to take the care that's required to avoid that happening to you. Then there are, of course, factors that influence the degree of that risk. We call them risk factors. So, for example, the intensity of your exposure to that particular thing. Are you very close to it? If you're standing far off from a transformer, are you likely to be shocked? No. If you are within a certain zone and there's a disconnection of wires on the floor, there is a possibility that you could. So proximity makes a difference. The concentration of that particular hazard makes a big difference. How you're exposed also makes a difference. If you inhale something, it may have a greater impact on you than if it just falls on your skin. And then your age makes a difference. If you're young and strong, maybe some things won't affect you as much as if you're a bit more mature. A female may have different exposures or different response or her risk factor relative to a male in the same space. So these are things that we have to bear in mind as we calculate your risks. So before any activity happens in putting up our utility scale systems, grid connecting and so on, it's important for your contractor, the utility, the developer to just do some basic things. One is to identify what those hazards are. Start at the source. What's the environment you're in? Then to make a decision about who are the persons who may be harmed. Is the secretary going to be harmed because she's going to be in the office all day and that she never comes out to the plant? Or is the lineman going to be affected? Who will be harmed? And to evaluate how the risk could affect them and to decide on the kinds of precautions that you're going to use. Of course, in risk assessment, you also have to record the findings that you discover. You have to make sure that it's properly documented. And you also have to make sure that you review your assessment of the risks, the hazards, and from time to time update, because the risks and the hazards that you face at the beginning of a project where you're looking at bare dirt is not going to be the same as when you have a live system generating. So that always has to be assessed. Now, a lot of these conditions and hazards may apply to other renewables. We are going to be focused on solar. And so when we just think very quickly, what are some of the hazards that we think are obvious? And I'm sometimes alarmed when I see contractors working and I wonder if they're not aware of their environment. So elevations, if you're doing a rooftop system and the code, building code, Caribbean Energy Efficiency Building Code talks about going as far as 5 floors up, falling from that height is a serious challenge. Survival is very low. Weather, we say we're Caribbean people, we're always in the sun. But if you're in the sun too long, no clouds, no water, then heat, dehydration and stroke could be a major issue for you. We mentioned the voltages are high, over 500 volts on the DC side. Glare is something we don't think about too much, but working over a solar panel that has a glass, tempered glass surface is exposing you to much more light than you would in a room or just walking on the beach one day. There are sharp edges, whether it be the railing system, the panel edges themselves. If a glass on the panel gets broken, you're exposed. Lifting is something that has to happen. There are many heavy components, your inverters, your transformers, your panels. All these things are heavy. And then, of course, out in the sun all day, there are things you could literally fry an egg on a solar PV panel if it is out there all day. So you have to be aware that these things can happen. Physical hazards at solar sites, mention some of them, but physical hazard defines a particular kind of hazard where there's an agent, a factor, or condition which could cause you physical harm. Now, radiation may not be one that we think of as physical, but remember, radiation is about packets or photons of light with light, and energy packets of different types of different radiation options. Then there's heat and there's cold and there's vibration with the tools you're using, and there's noise with the drilling and cutting, and then there are also things that could fall on your head. So these are things that we have to bear in mind when we talk about physical hazards. Then among the hazards, there are ergonomic hazards. Any condition that would cause you discomfort, pain, distress, an incident with your musculoskeletal system. We don't lift very well in the Caribbean. Watch people bend over rather than using their knees, using their back instead of using their arms. Little things that we need to learn, and they apply so much on the solar sites because, as I mentioned, a number of the system components are heavy, and they are not built for lifting. They're built to be established and secured, but getting them there is not why they were designed or how they were designed. So, but to be careful, let's use lifts and that kind of thing. Where there are repetitive motions, we have to be careful that sometimes you have to stop that motion, do something else, come back to it. Then there are safety hazards, and these just really speak to some unnecessary working conditions. Electrical wires from your DC panel just put down on the ground, it's beside another wire, you know, it shouldn't be that. That's a safety hazard, unnecessary. Or you have a cutting tool that has a shield on it and the shield has fallen off and you can't bother to replace it. That's a safety hazard. And those things do happen, unfortunately, at some of the sites. But I don't want to scare you, and hopefully you're not scared, because there are procedures for working very safely. There's a hierarchy of controls, as it's known by the National Institute of Occupational Health and Safety, and many others who use it. And basically it says, if you can eliminate a hazard, eliminate it. So maybe you don't need to work on a panel on a roof. Maybe you could do some, if you're doing a microinverter, for example, why not put it on the ground and then you lift it, for example. Substitution means you can replace the hazard or the measure of the hazard, then do so. So for example, a simple things like working very early in the mornings, when you're installing, or later in the afternoons when it's cooler. It doesn't mean that you stop the work, but it's just you shift the time. And the hazard is still there to some extent, but less. Engineering controls, things that you put in place to make sure that you protect persons in the event that they could be unnecessarily exposed. So for example, on a rooftop system, putting in railings so that, you know, if somebody steps back and they didn't realize they were so close to the edge, there's that rail to catch them, for example. And then your administrative controls, just managing the way people work, having rules and that kind of thing. We tend to put PPEs right up at the top, the personal protective equipment. PPEs are the last line of what you do to make sure that you work safely. So there's some specific areas and specific ways of working safely. There's a thing called a permit to work. Basically, it's a administrative control, the documentation, the planning, the communication of how you're going to work in a space. And you use this when you're doing hot works, you're welding, you know, some of your uprights or whatever it is for your solar systems, or you're working at high levels and getting approval, planning out your activities, and then of course having the PPEs for things that may fall on you, fall on your feet and so on, is a part of your permit to work. Energy isolation, I think, is one that many persons are very familiar with. Your lockout, tagout protocol. It's an engineering protocol. It separates you physically from the harm. And in cases like these, you want to make sure that the person who is doing the work, has the lockout, tagout control. You shouldn't lock out and someone else comes behind you and you know, undo that lock. And that this mechanization, this option for safety allows you to work, especially in areas where there are high voltages and so on. It's important to test the system, shut it down, confirm that it is at a zero state, so that even if there was an accident, an incident, there's no way that it can affect you. PPs, of course, are going to be important. Working at heights, very important. We tend to start thinking, oh, well, if you're so many stories, you know, hundreds of feet up. No, but working at heights and the principles around it begin at just 6 feet. Just 6 feet. Avoid that if you can, but if you must, make sure that the ladder is properly positioned. Make sure that you are wearing your harness and your lanyard, as you would see here. If he was to slip, he would be caught by a system and he would be protected. I put this image in. It's a very unsafe image. Folks who are not doing what they should be doing correctly. He's actually on the power line, by the way. It's amazing. Then lifting operations are going to be necessary at some point because solar panels are elevated one way or the other. They're on a roof, they're on a canopy, they're on a pergola, or even if they're on the ground, you know, they may be a little bit up. So it's a method of substituting. You have to raise it, the lift has to be done, but why use person and muscle power when perhaps you can use mechanization is an option for that. And of course, personal fall arrest systems are very important for persons operating in that context. Signage should be everywhere that there's a potential hazard, and it may read different things. You know, the OSHA standard, for example, speaks about having these accident signs and tags of different levels of awareness and danger, and should be easily read. And you see some examples here: high voltage, warning, and so on. These are very normal. Something that tends to be left out is that we may train our staff, the company staff, we may train our own contractors to do work. But then when we get a subcontractor to come in, sometimes we don't include these folks in the whole structure of occupational health and safety. It's important that they are in full compliance, almost as if they're your own staff. And if you find a context in which there are accidents, then you should have the right and you should do a stop order for such failures. They must perform as well, if not better, than your own team. Health and hygiene is something that we sometimes neglect. You know, we're tough, we can work in the sun, we can work all day, but you know, there are unnecessary hazards related to that. Persons, as I mentioned, can become dehydrated. You can have a stroke if that happens. People sometimes work long hours in the sun, in the open areas, and they don't eat properly. You know, fainting off a 5-story building is not a pretty sight, okay? And it's also important to have someone around who is medically trained who can facilitate. So we come down to the last part of, you know, working safely, which we unfortunately tends to turn the triangle upside down, and we do PPEs first. PPEs is after we have done everything else. So protect the eyes from the glare and from the sparks that fly when we're grinding things, and the sparks that fly when we're welding. Protect the heads from things which fall, from hitting as you go underneath structures, or from high voltages. A class B hard hat, for example, is very useful for that. Ensure that your team has shoes, because they're going to work on hot surfaces, hot roofs, hot spaces, but also make sure that you're choosing the right one. Don't just buy a pair of safety shoes because it says safety on the side. You're working in an electrical environment, and you don't want conductivity through your shoe or from your body down through your shoe, because electricity likes to go to the lower potential. Make sure that they're electrically non-conductive, as in no metals in them, for example. Gloves, appropriate gloves for cuts and tears, and make sure that you don't have slippage of things when you hold in our electrocution. We mentioned the fall arrest system with all its components, your lanyards, which runs here, your whole harness, your hat, everything, and anchored to something that is firm. Ear protection whenever there's grinding and a lot of noise in the space, heavy equipment moving around, and of course, in the COVID environment, respiratory masks. Let's not just get, N95 masks, but ensure that we're giving our teams masks which have filters and which have high air exchange, because being out in the open air, in the heat, working hard, makes it very difficult for you to function if you can't breathe. And then just in terms of who really uses these standards and follow these occupational health and safety practices, well, I just picked out 13 of some of the global leaders, and they are using different standards. Occupational health and safety standard 18,001, now replaced by 45,001. OSHA standards, in ANSI standards, and many others that give us the cues and the guidelines of how to operate safely in our environment. So I hope that will guide your team in your activities.
Thank you very much, Mr. Barrett. I currently see no questions, so I'd like to move on to Dr. Kun.
Okay, thank you very much, David, for those very important sections there, especially on the occupational health and safety matters, key ideas there. So what I'd like to do now is really enable the audience with some tools to take away, so that if you're interested in enabling yourself also to perform certain resource assessment or technical potential analyses and stuff at the same time, you can definitely have an avenue, right? There are a lot of online tools out there, but I decided to really look into some specific ones that are quite well known to us. So let's try to get some ideas here. Estimating technical potential for solar PV integration from a system-wide level. A question was posed earlier in the presentation regarding the ranking of the importance for certain parameters when we're looking at a resource assessment level. And I did mention that, of course, your solar irradiation data, we can get it from weather station data or satellite data at the same time. That's very important. An understanding of the grid network is also very important, because as you've heard by now, of course, we're dealing with high voltage system, high voltage three-phase balance system, as we like to talk about it. There was a nice power triangle that David showcased. It may have been skipped across a bit quickly for us, but we did see it in terms of the apparent power, reactive power, and stuff at the same time. So we keep that in mind. So let's just have a quick point here. It says the technical potential is a combination of the achievable power capacity, right? That's in your MW range, megawatt range, and the energy generation, that's in gigawatt hours, the energy at this point. So I always want you to always think about different types of REs carry what we call different types of capacity factor values. Right, a general benchmark value based on the technology and type of modules you use for solar. It can range from your 20 to 25%, 26%, you can get really good values and stuff there, all right? So the capacity factor is something that takes into consideration with your overall or full nameplate capacity of the system to give you that energy generation, right? Considers, production over the year, over its lifetime. You can then look at estimation over its lifetime at the same time, but it's for that available time at the same time, and suitable land area, because land area is something very important that we have to look at, because we can't just decide to run an analysis and determine that these particular areas are of good interest, of very healthy solar irradiation values. Yes, we're in proximity to the 128 kV lines. If we, dealing with Jamaica over here for a high voltage system, we're like, yes, we're those are all the parameters are needed. Those are not all the parameters needed. So suggest your introduction to it, right? So for a particular RE generation technology, given system performance, topography, environmental, and land use constraints, right, at the same time, at this point. So we're going to be looking at an NREL application online tool. That's one aspect. And then we're going to be looking at generating your performance report using PVSys, a software, PV photovoltaic software that we may have heard before. It's quite popular and something that you can get your hands on at the same time. So what does it provide? Technical potential provides an upper boundary estimate of a renewable energy development potential in a particular area. Now, of this diagram that you're seeing here, we're going to be just looking at the resource and the technical potential. And I would leave the economic and market potential for you if you do have time and you feel like you want to explore a bit on how to generate these systems for yourself. It will enable you the opportunity to move forward, right? So just let's have a look at this here, because it's very important, because we want to get to the technical potential and we know a bit about the resource potential, right? Resource potential, but there are a lot of many other layers. Right? If we think about it like that, some of us maybe may have dabbled into GIS, or even experts, some of us here may be experts in GIS, and we all know about the correlation of different layer maps and stuff at this point in time, right? So the solar resource estimation and analyzing solar resource technical availability, that's what we want to get, right? So further analyses can build on the technical potential to evaluate the RE potential in relation to cost and other economic market considerations, right? So let's attempt to use this tool now. So let me come here. As I say, always check on your QR codes. You can go directly in. I will disable the audio here. There will not be any audio. I'll just do a quick check. So we go to our RE Explorer mapping tool option. We go to our RE Data Explorer. I checked for CARICOM members, and it was only Haiti on the map in terms of the availability of data that we're looking at here at this point. So you go into the software itself, and what we're going to be doing here now is running a search for the particular area, generating layers. This to give you an appreciation of what goes in to create that technical potential aspect there, right? And you can see a list of different parameters are coming up. So what I decided to do was, you have to think about in terms of what's the dominant factor that you have, and then you're going to overlay that dominant factor with many other parameters, right, or many other layers. So we have the direct normal irradiance at that point. There are others that you can choose based on the data availability. And you can see, I'm just going down here quickly showing you, we have environmental aspects, the administrative in terms of the roads, the boundaries, because you have to think about it at the same time, accessibility to that site. You need roads definitely to reach. And if you're going to have to clear areas down, that's going to give you even more expenses adding on to your capex, right? So I've gone on to add other regions, lakes, rivers, your land use. We can check on a separate video on next one here, and you can see piece by piece the map is beginning to populate more and more. You're getting a bit of appreciation now, right? So I zoomed in here and let's have a look. Really nice area. First of all, it strikes you healthy solar radiation. The grid network that you're seeing here, it's accessible. You don't want to go looking into areas where it's the heritage sites, or at this point in time, other land use or protected areas at that point, right? And then you can say, okay, well, on an estimation, you want to have certain areas of interest, right? And then this is just a first point of use. You can then integrate land use data a bit more later on with these ideas and overlay them to just keep building on what this first estimation is going to be all about. Now, of course, you have to visit the site and perform other site selection analyses at this point, right? So let's have a quick look here. This is another short video, just one minute, so that we're going to be looking across here. In this one, I decided, let's look at the land use data. So I have a benchmark idea of my area of interest that I just used. I'm going to do the same thing again. Because the land use data and the solar radiance are dominant factors, even if we change the opacity, it's not going to show you clearly, but it's a toggle function that you can definitely explore. And let's go through the same process. Let's begin to populate this land use data map now with our other parameters of interest, right? So let's just give the video a couple seconds there and begins to populate again, and we have this general idea of certain areas. You can then look at what areas would be good if it's arable land and you need permits to access those areas, if it's near certain sites of interest, and there's a list of permits that go in just for accessing land locations, right, at that point in time. And this is something that goes across the board for any sort of type of installations of power plants at this point in time. It definitely has this agenda of rigorously analyzing what you're providing to this area if you're not negatively affecting it at the same point in time, right? So I hope that did excite you a bit on how you can apply this. And now I was going to show you quickly, if we're looking at another performance reports, right? Performance reports. So we looked at Haiti just now there. Why not let's just do a quick PVSys analysis on Haiti. So you can actually get a nice free trial on a PVSys for you to explore. David in previous sections mentioned these ideas, and it's very important. When you're looking at the voltage that is going to be generated at the end, the matching of those with your inverters, and meaning that your inverter needs to be able to handle the amount of power that you can be generating on your PVN at that point, right? So just allow me to quickly exit and re-enter here on the actual software itself, right? So I'm going to go on my PVSys trial here, and you should be seeing my screen here, right? So I pre-recorded this, and I built it before so that we can quickly move through at this point, right? But generally, what you're going to be doing is looking for available data to fill and build the upfront system. And if it isn't there, there's a library, other categories of metadata that you can use, because we know solar radiations is a dominant one at this point. I'm just going to fast forward the ideas here, and this is the toggle functions where you can begin to customize, right? And be basics 101 of your solar PV in terms of your tilt angle and stuff. You look at the latitude that you're associated with. At some points, you don't even have to use the exact angle latitude that you're located at, because us in the Caribbean, we're blessed with so much solar radiation. Just look at what Content Solar, I believe, they position theirs at, say, around 12 degrees, even though Jamaica is around 18 degrees or thereabout, right? Because even at 12 degrees, you can maximize, you can get as much, right, as you would have at that point. And plus, it also saves on costs when we're looking at other ideas of, your mounting posts, and less materials is going to be used overall. And then we spoke about Content Solar, is the number of thousands of panels that you're going to be using. So the cost of that is a big cost reduction that you can do at the same time. If you can have less, you reduce that angle, right? So less material, and at the same time, your performance is going to be there. That's exceptional at the same time too, right? So, right, you can just go through the toggle function, look at these ideas. If you want to fix it, if you do have it at true south, you can leave it as is. If you want to set those angles in, you can look at that up on your own time. You can go into the system itself. And this is where it becomes really interesting. You can set it, say we want to do a 20 MW system, we want to mimic that of Content Solar, right? We can enable it. We can then go and search for a type of PV modules that we're looking at. There's a huge array and listing of different types of modules that we're going to be using there. And you could have further specifications of the types and stuff at that point. And what's next, very important idea here, inverters, right? Same thing. So you go through all those ideas of those inverters, inverter sizing at that point in time. There may be some troubleshooting that needs to be done based on the matching of the overall inverters to the power generation at that point. And then you simply just go ahead and look at other detail losses, because when we're looking at systems this large now, losses are uploisted. They're basically enhanced even furthermore. So on a simple approach, just a quick skim through here. I decided to go with some default setting values, some ones of interest that we might think about, or we tend to forget. We always have to think about that degradation factor at which the performance of the PV systems, degrade per year, roughly around 0.4%. Yeah, they're just about per year, but we have to look at those ideas of performance, and then we can set in on availability, because this is not going to be 24/7, 365. We need to have 1M, right? 1M cost is something that goes in at the same time, operation and maintenance costs. You can have those duration in terms of days and number of periods. You can set it, so you can customize your system as best as you want at that point in time. I'm not going to look at the self-consumption and storage at this point. This is something that you could explore also at that point, because then you could also have site consumption at that point. energy or peak shavings and all those ideas. You run your simulations. I'm not going to run it here because it might just take a bit of time. So let's just cancel this and let me show you how the report looks like. So I've also saved this separately as a PDF. Okay, so we are up and running here. This is a general idea of what's going to be happening here, right? Because we're interested, what are the outputs? What are the outputs of this quick analysis that we're looking at here, right? Those are just refinements and just technical information that we've inserted into the system itself. Let's look at some outputs, some graphs, right, at this point. We have the normalized energy versus throughout the year. Now, this is a very good plot that we can use here because we could actually look at the production at that point, have an idea of the system losses and collective losses monthly through the year. This is something that's very important, and I'm sure the JPS rep might mention something on this and how important forecasting or predicting of what you're going to be getting for future energy productions and performance ratios and stuff at that point in time, base overall, balance sheets at that point. So I'm going to quickly transition over to David now because I believe, let me just do a quick check here. That will be it for my side of things. Yes, and we're now back to David.
Just confirming whether you want me to go ahead or if JPS score is presenting at this point. You want me to go ahead?
Sure, you can. Go ahead, David.
Linker, I think you would have been scheduled at this point. So if you're ready to go.
All right, if you're ready to go by me, all right, no problem. Just let me know if you guys are seeing my screen here.
Yes, we're seeing the screen.
So we're good to go. Everybody see my screen?
Yeah, we're seeing the screen.
Yes.
All right. So, all right, so after that, good morning, everybody. So quickly, we will be looking at the utilities perspective. Our experiences so far with grid scale solar. So that I give you guys a full bandwidth. So, GPS, as you know, basically a vertically integrated utility company, 80% owned by shareholders located in the Far East, and the remaining 20% are owned by government shareholders. Yeah, yes, David.
If you can hear me, perhaps if you have any other, any other device or program working, you may want to close it. The voice has a little bit of a bubble in it. It's not as clear as earlier. So just to make sure you have enough bandwidth.
You hear me much clearer now?
Keep going and we'll confirm.
Okay. All right. So let me try and amplify my voice a little.
You're clearer. You're clearer.
Okay. Okay.
Thanks.
That's all. Right. So basically, what you're looking at here is just the ownership of JPS. 80% shareholders from the Far East, 20% by the government, and the installed capacity of our grid is about 1,030 megawatts, with our highest peak demand to date of 666.7, right, back in September of 2017. The market is so split up right now that JPS only owns about a third or 40% of the generating assets that are on the grid. Of that 1,030, 337 is owned by JPS. And we serve about 650,000 customers of our 2.7 million population. So in 2020, right, this is how our electricity demand looked like. in terms of from an energy perspective as well as from a generating technology. So based on what you're seeing here, we're pretty much still dominated by fossil fuels, but primarily in 2016, we did a switch to natural gas, and we're almost up to 6% of our generation production from natural gas right now. Renewable energy stands almost at 13%, 3% of which comes from grid scale solar, and this is on energy. So let's walk you through the JPS history a little bit here, just to give you that context. So typically, let us say our average day peaks are around 580 megawatts, of which 17% of that might come from wind on a typical day, and in terms of capacity, 10% from solar, which shows almost 27% of total capacity coming from variable renewable plants. Now, this is not primarily a challenge, but when you get into the order and magnitude of lower demand days, especially on weekends and on public holidays, you can actually hit penetration levels of almost up to 40%. Now, based on some articles that were done previously, it shows that once you have variable renewable penetration exceeding more than 10%, that it will present some challenge for me, the grid operator, right, in terms of how you manage frequency and voltages, some of the things that Randy was talking about earlier. And to the right-hand side here, you can see how JPS and Jamaica have been moving up in terms of variable renewable penetration, especially for solar in 2016 with content, and then in 2019 with the commissioning of Paradise Park or the 8 Rivers facility. So just to show you a typical day and how these variable renewables, especially solar, behave on our system. So what you're looking at here is not the results of somebody's ECG report, but this yellow line represents how solar plants behave over a typical day. And what you're seeing now is this constant up and down, or this intermittency that is caused by occasional cloud cover over almost an 8-hour period, starting from about 6 in the morning right up until 5 in the evening. Now the gray, blue, and orange line represents wind. So you see that solar has a little bit more variability than the wind. And what this introduced for JPS is that this variability of power, because we're in the business of matching generation to customers' demand, this gives us a perfect indication of our grid frequencies. So what we started to see, we have a lot of frequency fluctuations. And as a grid protection mechanism, we have certain frequency set points on our grid to say that if the frequencies hit these set points, then this amount of customers will have to be automatically disconnected from our system in order to try and restore this balance. In fact, when we commissioned our first solar facility back in 2016, we saw almost a 40% increase in customer outages due to the intermittency that we were experiencing from that solar plant, right? And that was a huge challenge for us, and especially our even worse inconvenience to our customers. Another problem that we experienced with solar and renewable penetration is one of the maps that you saw earlier from Dr. Kunkun is that most of the resources for solar and wind, right, they're located in one particular area or one particular side of our grid. So what you're looking at here is almost a transmission system layout for a system, right? So what you have here is there's a dashed line that represents how they separates the corporate area or the city, right, area of the country, right? And then there's another section of the grid, which is called the rural area for our system. And this is how our generators pretty much are tied in to supply these demand, which are these cute little light yellow bulbs here. The solar plants are typically on this plant side of the grid, right? However, most of our customer, 60% of our customer base exists on the right-hand side or on the eastern side of the grid. So what you might see happen on a day-to-day basis is that the more energy you take from solar and other renewables, in addition to the other thermal plants that are located on this side of the grid, as well as we have some hydro units, is that it will cause some of these thermal units, especially those within the eastern part of the grid, to be displaced. And what you will find happening is that you have a lot of transmission congestion issues because you're trying to move power far from the west into the east. And one of the things you require to support this is probably to upgrade transmission lines, some generation suboptimal dispatching, or dispatching generator units outside of what is called least cost in trying to balance the flows on your system, right? And if you realize that there's an energy storage unit that typically what you have been taught and what we have been experiencing is that most people tend to locate their energy storage system closer to their renewable facilities. But here at JPS, we decided to put it in the eastern area. And as I go down the grid, I'll explain to you why. So in summary, here are some of the grid issues that we were facing. We experienced a lot of automatic load shedding since 2016. We have quick start units that are located primarily here on the western part of the grid. These are very expensive to run units, right, with poor efficiencies, but they give us very quick ramp rates and quick startup times. So we have to be using these units a lot to chase down the solar plants. In addition to that, with the constant back and up and down in all these generation units, it reduced their thermal efficiency, increase costs, and also increase the amount of wear and tear and hence maintenance activities that you had to do on thermal machines, right? Steam, combined cycle, gas turbines, diesel engines that we have in our fleet to support them. And hence it increased the cost of dispatch, which would have increased our production costs to the consumers. In addition to that, another phenomena is that we saw was we had voltage management concerns. Now, typically, a lot of persons are focused more on renewable plants, solar PV, to provide it with real power or megawatts and not necessarily megavars. So most of the contracts that we signed in the past, these plants were providing us with real power and not so much VARs to help us with voltage. So when these renewable plants were displacing the thermal plants, what we saw is that the thermal plants, which can give you VARs and voltage support, once these were displaced offline, you lost the ability to maintain voltage support. Now, why it became critical for us to address this problem as quickly as possible, in collaboration with our regulator and our government agency, which is the Ministry of Science and Energy and Technology. The IRP that the government did in 2018 completed that draft up to 2020, right? Saw where in at least within the next 3 years' time, we will be moving from almost 13% up towards 30% on renewable penetration. So hence, this kind of problem is something that we must address. Thankfully, as I said, that with a collaborative effort, JPS with the GOJ, Government of Jamaica and its regulators, we came up with some solution sets which help us to not only manage this intermittency need, but help us to leverage all the benefits that we can from renewables. Because even though I was showing you challenges before, renewables are a good thing to have. And for small countries like us in the Caribbean, which are mainly dependent on imported foreign fuel for generation, having a renewable source of electricity is a very good thing. So the only concerns that we need to do is to ensure that we can manage the levels of intermittency and reduce disruption to our customers. So what we did is that we improved our situation awareness tools for our grid operators, our guys in the control room. We embarked on a program to replace some of our age generating fleets, which did not have the ramping capabilities to keep up with some of these renewable plants that are moving up and down much quickly. Also, we implemented an energy storage system at the end of 2019, which is first of its kind in the Caribbean. And at that time in 2019, was the largest hybrid energy storage system in the entire world. Right? In addition to that, we incorporated the use of renewable forecasting tools to help us to be more proactive in terms of seeing renewable intermittency coming from afar and be able to put plans in place to manage it before it resulted in disruptions. Right? So we use these renewable forecasting tools to help us to manage real-time operations, to do a little bit of dead planning, and weekly forecasts used to manage our operations in terms of even anticipating of when we'll be getting more wind and solar resource, and hence be able to schedule our maintenance activities on our generating units. In fact, one of the providers of our renewable forecasting tools, we have this kind of irradiance map, where what you're looking at here is a typical day. Red means very good sunlight, but these blue lines that you're seeing are clouds forming. So what you can see is that as the day progresses, you can see how clouds are being developed or being formed and how they're moving towards this solar facility. Hence, you can predict the drop-off in this facility when it comes up. Another thing that we did, as I mentioned before, was that we installed a hybrid energy storage facility. Why hybrid energy storage, you might be asking, is that hybrid facility composes of a lithium-ion battery installation and a flywheel. So what we wanted is to achieve the best of both worlds. We know that lithium-ion batteries are not very ideal to have them up and down and constantly cycling, and this constant cycling also improves the rate of degradation. However, flywheels can be cycled up and down until you die, right? But the difference is that they don't have the high amount of energy density or power density that you can get from lithium-ion batteries. So combining the lithium-ion battery with the flywheel, everything here turns green, and we're able now at first to use the flywheels to manage a lot of the initial cycling operations due to intermittency. And then if we need to go a little bit further, then we'll use the batteries on the back end to provide a lot of power to manage the intermittency. What does this all mean for us? Well, just to paint a picture, in 2016 to 2018, comparing that time to 2020 and where we are today in 2021, we saw almost a 90% improvement in our reliable KPIs, meaning that we reduced most, if not all of the outages caused by renewable intermittency by installing our 24.5 megawatt hybrid energy storage facility. This storage facility also helped us to manage some loss of generation events associated with thermal units. And interestingly, as I said before, based on the position of the storage in our grid, it was able to help us with voltage support for those thermal units that were displaced offline. So our energy storage unit provided us with good frequency regulation, excellent spinning reserve support, and it provided us with voltages both in steady or transient state at short-term movements for voltage support when the grid requires it. In fact, we use that energy storage in a major restoration after a system incident in April of 2020. What does that look like? This is what it looks like, and this is reality. This is not a simulation. On the right-hand side, you would have seen the simulations that we did before. And on the left-hand side here in black, it's an actual event on the grid where this white line showed us the output from the Paradise Park facility. And what it shows here is that you can be going in nice and cozy with your renewables until a cloud comes, and then it does a sudden drop off. The yellow line here represents the grid frequency. And what you're seeing here is a sudden drop in the grid frequency because we are losing this solar plant. However, because of good fast interaction by the storage, what it did, it helped to dampen the rate of decline of the system frequency, maintain it at a stable limit until the other thermal units were able to catch up and help you to restore your system frequency back to within nominal values. What would have happened in the past would have been the frequency would have continued to decline until it reached this red line here at our first under frequency point, about 49.35, which would have unfortunately resulted in customer disruptions. As I said before, 90% of that now is behind us. And what we're seeing now is this gradually smoothing out of our frequency until we can get it back to steady state. So the grid operated experience here in Jamaica is a good thing. It shows that we can facilitate more solar PVs, but these things have to be combined with good proactive studies and analysis, a good mixture of thermal or firm units with the solar PVs, as well as energy storage. And hopefully as the cost of energy storage becomes much cheaper, it will enable us to facilitate the integration of more solar PV, which will give us the benefit of deferring expensive generation and imported foreign oil, and basically help to lower the rates to the customers as the future progresses. So that's it from me, guys, unless there are any questions.
Thank you very much, Mr. Small. We have a few questions. First question is, what PV solar designing software would you recommend? The options given are home or red screen or PV Assist, but they're also asking if you can provide any other that can give accurate results.
Well, the good thing is that we have Randy on this call, because that's not one of my areas of expertise. So probably Randy could be the best person to say, oh,
Yeah, I'll quickly mention, yes, so the Red Screen Experts gives you more of that risk and financial modeling aspect of it on the back end. The Homer is really good, for those microgrids and looking to integrate it. Homer is actually one that's really stood the test of time. That's really good also. The PBSys is a much more specialized field, whereas the Homer and the Red Screen, you can use many other different types of renewables and energy generations and stuff. In terms of training and stuff, that's something we can check up online, or you can always contact me and we can have a discussion on that, looking up on those aspects, because I'm doing some research and stuff also on those Homer applications at this point. Yeah.
Okay. All right, thank you. All right, Mr. Small, I believe these are yours. Does your solar supply ever surpass 10 to 15% of your grid load? And how did you manage the required load swing? Thermal units?
well, the good thing is that I don't think we have ever passed 10 to 15% of supply. So the total capacity, we have come in that range on public holidays, right? On 1 or 2 occasions. So how did we manage these load swings? Is that the energy storage solution that we have, it provides you with good frequency regulation, or a function that's called renewable smoothing, where it can detect whenever you have sun ramp rate changes, right, in the renewables. And what it does, it basically counters energy storage, puts power into the grid to counter that sun drop off in renewable output. And it will do what is called smoothing. It will basically, instead of making it a steep slope of decline for your system frequency, it will result in that decline being very much shallow, right? And hence giving the thermal units the opportunity to manage those load swings. In addition to that, the thermal units also provide good governor response. So using the storage first to make the ramp rates a little bit more smoother and gradual, then the thermal units will pick up on that. Based on their droop settings, it is more manageable, and they can help now to manage the fluctuations that the intermittency that the solar plants introduce onto the grid.
All right, thank you. So, you mentioned that you use battery and flywheel hybrid for the energy storage. Just asking the size and if you can comment on the cost efficacy of using these types of storage.
All right, so the 24.5 megawatt total installation capacity, 3 megawatts of which is flywheel and 21.5 of it is lithium battery. The total cost for that project ranges somewhere about $25 million. So let's look at it in a sense of $1 million per megawatt, right? The good thing, as I said before, is that global trends are projecting that energy storage prices will decrease in the future, right? So it will reach to a point in where energy storage applications will become much cheaper than you actually use in a thermal installation.
Okay, thank you.
I'd like to just quickly chip in there. Yeah, it estimates are around 2030. The vanadium flow batteries and stuff that can go 6-8 hours extra at night, they become much more cost competitive around that 2030 landmark there. So definitely it'd be much more attractive for batteries and stuff integrated soon. I hope that JPS in the future is also looking for more energy storage, because it's definitely on a very good idea to have that with the drive that Jamaica is going for renewables.
And that is a part of the plan as well. And as I said, in collaboration with the IRRP studies that the ministry did, right? That's one of the things that we're looking to do, to see in order to support the proliferation of renewables. to introduce the more energy storage in the future, especially as the price is reduced.
Excellent.
All right. Thank you very much. And we'll move into the final segment now with Mr. Barrett.
Yes, excellent, Lincoln. You know, I appreciate the fact that, and I hope everyone here can appreciate the fact that the modeling that is done is very important, not as an academic activity, but for actual performance. And as Lincoln was able to show you, that being able to predict the potential weather changes, for example, helps significantly in the quality of the power and how the operator performs. And so, you know, and he also talks about storage. We're going to talk about that a little bit more. So all that we have spoken about so far has to be tied in with the matter of project financing. And, you know, developers and investors, when they're thinking about the options, whether they're going to go back to fossil fuel options, or as Lincoln has supported the need to go to cleaner options, renewables, solar being one of them, you know, they tend to look at a number of parameters. One is the fixed costs. You know, that's a cost that comes right up the heavy capital costs, equipment and the land purchase and the financing that you need and interest rates that are tied to that. And you get your project managers and, you know, you get your whole power plant constructed. But you also have those variable costs which keep running once your plant is up. You're going to be using fossil fuel, diesel, or natural gas, etc. How you operate the plant, schedule maintenance, your manpower, and your emission charges. We don't have those in the Caribbean as yet, but certainly those are going to appear. And then, you know, when you look at those variable costs, if you look at the average variable generation cost for a utility scale system, and you're looking at variable generation sources like solar and wind, for example, that's going to affect part of your decision. What cost do you want to carry day by day, month by month? And, you know, within the Caribbean, when we look at the utility scale, grid connected variable generation options, we're seeing prices running between about 7 cents and 13 cents. Another parameter is looking at the average variable generation and distribution costs. So for those that are not grid connected, but those that are not utilities, I should say, or they're not PPAs or IPPs, then they might just connect on the distribution line, and there are going to be some losses along the way. So you may want to factor these two. The numbers are running about the same, 7 cents to about 18 cents within the Caribbean as we look at those parameters. So when you then compare the generation cost options that you have for different types of technology, and you do the levelized cost of energy. Levelized cost of energy is a way to sort of, as it were, level the field between, you know, the fuels that you might use, fossil, or the sun that you might use, which you don't pay for, the structure of a running diesel plant, and the structure of a wind turbine or solar system. And it's a way to just bring those costs to a number that you can compare. You find that in terms of dispatchable utility scale system, that means you have a base load, you have a reliable supply that you can bank on, you can predict, you can charge for without any challenges. Then you find that the conventionals seem to come up front in terms of having lower cost, 10 cents, 15, 12 for geothermal, and so on. When you add battery to the system, the levelized cost of energy is a bit elevated above some of them. But note, it is, for example, below conventional combustion turbine systems. And that's something for us to pay careful note to, because all the things that Lincoln already mentioned in terms of reliability, in terms of smoothing of frequencies, in terms of quality, you actually have a benefit that can be valued perhaps from a different set of matrices. If you're looking then at, should I just add variable renewable generation and the levelized cost of energy? Sure. Solar comes in right there with the best of the prices, wind also. And when you look at small distributed generation systems, the residential, those prices are a little bit up because of course, you know, the scale does make a difference. When we drill down into some of the component costs of a solar system, you'll see the others there. And when you go to, this is from IDB, they did a sustainable energy path study for the Caribbean 2020. And this is taken from that. I took out the fossil side just to condense the presentation. But bear in mind that when you look at solar as a variable option, and you look at a 10 megawatt system, the unit capital cost is about 2.4 million per megawatt. Timeline 20 years, capacity factor fairly good in terms of where variable renewables are. When you look at other sources like biomass, waste from energy, geothermal, which might be put in the base load category, you know, they have higher capacity factors. But when you add storage, then it improves the value of solar PV. So definitely we need to be looking at more storage, as Randy raised. The fixed costs are, you know, not too far among the variables. They're higher in some cases for the base loads. And then look at unit cost of the resource. It's zero. So that's going to be taken out of your running costs, and also your variable operation and maintenance is also going to be removed from your cost. But bear in mind now that for your renewables, one of the things is that they're often space intensive. So you're going to have to look at other costs like your land lease and your, you may need a substation, you might need a switching yard to make connection to the grid. Randy already mentioned road infrastructure has to be included, and you will have legal costs and other costs to be considered. I think I was quite right that, you know, battery storage costs have rapidly declined over the years. There have been technology advances, and Randy mentioned that. And so just looking at lithium alone, you know, we're starting out from anywhere from $650, $620 per kilowatt hour down to about $380 per kilowatt hour for a 4-hour lithium ion system. And as you can see from the National Renewable Energy Lab, their chart on the right-hand side here, you can see if you have a sort of high range scenario, those costs will continue to come down, but surely will be higher than the mid-range. The mid-range, you know, sort of looks at the best case, worst case scenario. And so you can see that the cost for utility scale solar PV systems, it's looking very good in terms of the future for mitigating the intermittency on the grid. When you look at the breakdown of costs in terms of the percentage of your total cost for your solar PV facility, you will see that a lot of costs, maybe surprisingly, is on your modules and on your structure. Part of the reason for that is because you want to make sure it's rugged, it's resilient, you can tolerate the weather, the climatic issues. And then, you know, there are a lot of little pieces. There are, you know, there are footers with foundations, and they're uprights, and, you know, a lot of steel and bolts, and your panels have their own costs and so on. So those tend to be a little bit high on the cost side, percentage-wise. But it's also very important that when we look at resilience, that we bear this in mind, and a lot of the resilience components are pegged there. We have to think resilience because we know that our environment and our climatic conditions are getting worse.
There were evidence in 2017, and it's been a long stretch since we've had the Gilberts and all the other events. And it's important now that we start planning not for Cat 3, but 4 and 5, right? And as I mentioned earlier, adding resilience to your facility or utility grade solar PV plant or a wind plant for that matter will increase the capex by about 20% compared to your standard project. But we have to bear in mind that there are a number of larger projects which have already considered this. Content Solar is one. They have done their flooding and their wind surveys. They've raised their panels significantly in the case of the potential for floods. They have ensured that their racks are able to withstand severe weather conditions by having their screw piles and so on. But for the grid, one of the things that has been put on the table is burying some portion of your distribution lines. So you want to be careful. Having a buried distribution line in a floodplain makes no sense. You get water intrusion, increased risk, you're going to have problems. But let us say that there are areas which might have the right slope or right elevation, then you look at underground lines inserted into that package in your overall cost for your grid operation. And there is an increase, okay? There is an increase. And your standard overhead lines cost much less, easily a fifth of the cost of doing these underground lines. But when you talk about resilience, being able to bring your system back online quickly, that's another cost computation that you have to factor into the whole picture. So what's the cost of resilience? The IDB did some work and they confirmed, for example, in their studies that, when you add levels of resilience, for example, the additional underground distribution lines, when you reduce the damage to your lines in a hurricane, when you look at strengthening your solar structures, more bolting, cross members to prevent collapse, when you look at the economic loss that you have when power outages occur, when we think of the Dom Rep and Puerto Rico and others that lost almost a year of their life, as it were, because they couldn't get their systems back up. The study showed that the net benefit is over 4,315 million US dollars different just by putting in these resilience components. So in trying to finance the projects and trying to make sure that they're resilient, we have to look, where is finance available? So project finance for the region tends to be a little difficult because we are small islands, our projects are small in scale, and so sometimes, the larger investors look elsewhere where they can get, hundreds of megawatts in any one go. But finances are available, especially that there's a concentration on climate change mitigation. When we realize the significant amount of solar resources that we have in our region, we are able to attract finances, especially from our development partners who pay attention to those things. UNDP and the UNEP, for example, using the Global Environment Facility to facilitate a number of small distributed generation systems, usually a smaller range within the commercial. In Jamaica, the commercial band is 10 to 100. Other islands have their other ranges. But the development partners tend to facilitate within this frame. We also have other development partners like USAID, which has put out its public-private sector alliance program. It's putting in $4 million to enable private sector to get over the renewable energy barriers, put in their commercial scale projects, whatever is approved under the acts and regulations. And they're doing projects in other places in the Caribbean. But it's not just our development partners, giving grants or low interest funds, but you also have commercial, private, national donors or financiers who are putting in collateral within the region. Some of them you are familiar with, European Development Fund, the China Development Bank, for example, the Department of International Development from the UK. And so these are entities which are using their commercial departments to generate opportunities for their nationals, but we as a region benefit from the opportunity to access those funds. A lot of our projects have difficulties getting past the funding start gate because technically they're not sound, or we may need to build capacity. And so it is possible to get technical support to get us past that place. I mean, CCRE, for example, is providing a lot of capacity development in moving us forward along this line in our policies, in our trainings, so that we are able to deliver the amount of renewables that we have in the policy targets, which we saw at the very beginning when we started this morning. So you have your CEDAs and you have your GIZs, NRELs, and others who provide grant funding, technical support, helps us with our financial assessments or feasibility studies. Because without these grid scale integrated solar systems would not occur. We're also getting direct international private sector financiers who want to invest in the region, and different mechanisms are used, special purpose vehicles. So for example, a project in St. Kitts, where they are looking at 350 or 35.7 megawatt solar plant, and they're looking at battery storage also. In this case, the state is not putting any funds in, it's providing land. And we don't know all the details of their agreement, but the point is that the private sector entity is putting up that fund to develop that facility. And that's one way of getting your projects funded. But then you also have public-private partnerships where the government partners with a private sector entity to put those projects in. So those are other options. The commercial banks are coming alive now. Our development banks are becoming more creative in facilitating us and helping us get past our boundaries, because they are recognizing that renewables definitely have achieved grid parity. They recognize the importance of the global clean energy commitment and campaign. They recognize that the national ambitions are quite strong and they are much clearer now, they're refined, and a number of fossil systems are being retired. So you have your Eastern Caribbean Bank, you have your CDBs that has done a lot of work within the region, your IFCs and your Caribbean Basin Sustainable Energy Fund, which is also involved. You have others, you have OPIC that facilitated the BMR and Content Solar in Jamaica, relatively large projects for us, or size. IDB has been a friend of the region for a long time. CARICOM, the Caribbean Renewable Environmental Fund, is huge. And then, of course, you have the French developers for a lot of our Eastern Caribbean islands. So just to close, and I'm hoping that you leave this workshop with a positive note, because utility scale solar PV is very mature. You should take that away. We have the technology, we are using it, we are replacing a lot of our fossil options, we are meeting our renewable ambitions, our environmental and our financial and environmental sustainability goals using utility renewables, but not just using that, but ensuring that resilience is part of that package. And we're also using the opportunity of battery, as Lincoln spoke of, as Randy demonstrated, the opportunity for batteries and the reducing costs of battery storage system and battery flywheel for Jamaica, for example, to overcome some of those intermittency conversations that would have happened, decades ago. And then, of course, the type of funding that's available now is quite diverse. Commercial options, green debt options, grant options are all available. And with all of this, we are able to move some of the technological capacity and policy barriers. So we're in a very good space, and want to say thanks to CCRE for facilitating this workshop. Thank you.
Thank you very much, Mr. Barrett. It's very important when you're discussing any interventions to mention financing. And it's also important to note that the CCRE provides technical support and project financing through its flagship program, the Project Preparation Facility. There's a link in the chat where you can go to find out more about it. We have a few questions. I'll just read them to you right now. 1 second, please. Okay. What are the advantages and disadvantages to have a distributed generation, individual PV systems at residences and commercial buildings that is spread across the country versus a single large IPP solar plant? That is, have the PV spread over many suppliers where the client is paying for the investment versus large plants and having to pay for that investment.
All right. I'm hoping Linkoy will come on this one also. But what I'll begin by saying is that we do have line losses. The technical losses, as it's mentioned in the Jamaican scenario, and other countries have their measure of technical losses. Some of that technical loss could be mitigated or reduced by having distributed plants in different locations, as opposed to a central system that is sending a lot of power over long distances of line. So that's one huge benefit. Another benefit is that if you have large central systems, if they go down, the impact on the entire network is so much more severe than if you have multiple systems. And I won't put a number on how many systems because each country is separate, but it allows the utility and the operator to continue putting in power into the system in a controlled way, while perhaps a central system might be down. Also, what it does is it takes off some of the pressure from the central operator. It allows them some amount of downtime for maintenance and so on, because you would have other systems in different places. And of course, we have the green benefits of having the renewable systems in operation. So there was a second part to that question, I think. One was...
I'll just repeat it for you. 1 second.
Thanks.
So
and Lincoln may want to come in after.
Okay.
Yeah. What are the benefits to have the PV spread over many suppliers versus a large plant?
All right.
And having to pay for the investment. Sorry about that.
Well, of course, the cost then is also a plus, because if Linkoy's company now has to go searching for large amounts of funds, it's going to affect their commercial viability, as opposed to using systems like net billing, net metering, tariffs, feed-in tariffs, so that someone else is carrying that cost, but nevertheless providing power on the grid that the operator, the dispatch operator, can utilize to supply. Linkoy?
Right. So pretty good. You did a good job on that, David. Having as I said during my presentation, and I hope I'm not distorted again, but if you have most of your PVs are grid scale concentrated in one area, where one cloud can basically just come and wipe out everything, right? Then it will present a lot of challenges for us on the grid to manage that. Versus if you had the PVs not only distributed across a wide area in your transmission network, but also on the distribution, you'll be able to manage those flows, relieve any potential transmission congestion issues, as well as, to David's point, if you're serving the customer's demand right there instead of moving power across a distance to get to that customer, then you will also reduce levels of technical losses. You will reduce the need for transmission investments, which will basically help to reduce your overall electricity costs. And then from another perspective, just a matter of resilience. Let us say that, God forbid, you should be impacted by a hurricane, right? If we had solar PVs backed up by some energy storage, right, to firm up that supply spread across the grid, then it means that instead of, when we're restoring the system, to be restored from large central generating locations to try and get to customers on the western side or on the eastern side, wherever they are, but there's a great distance of transmission between them, it means that you'll be able to get to these small pockets of load very quickly and start to rebuild your customer base quickly instead of waiting on your transmission system and your distribution system to be rebuilt before you can actually restore. So it also improves your level of resilience once you can have more distributed generation spread across your system, which basically leads to the development of what you call microgrids.
Thank you very much. Thank you very much. Next question would be, how much power could be generated from the waves of the sea compared to solar?
That one's a little tricky. So a study was done in Jamaica and also looking at the Caribbean. We were normally or previously ruled out of using marine power or blue energy. But the wave energy study that was done, which means that by using the undulation of the surface, you're actually able to use a mechanical system to generate power. And we were found to be just sort of right on the cusp of what would make a system technically capable. The cost is going to be much more than the renewables that we have, in terms of the levelized cost of energy. But that is coming down as any other technological activity, improvement on systems, getting rid of the bugs, passing the proof of concept stage. It's improving, but it's going to be above that. It's going to be above the 20 cents per kilowatt hour right now. And because we are just coming in at the floor of what's possible, right now it may not compete as a grid option, but it's something that we should continue looking forward to because, for example, Barbados on your Atlantic side have very strong waves, which would have a better potential than, for example, other more Western islands. So something we should keep on the books.
Thank you. Any other inputs?
I could quickly chip in there. Just on the previous question, also excellent points, because if we're looking at 1 kilovolt of power generated at a large plant, the technical losses from that is going to be reduced as compared to if you had that same amount generated on site, you save from all those losses. So it helps towards that grid efficiency and reducing fatigue on the grid itself because it's less overall power that needs to be generated at that point. Just one other point also now with the OTEC, I believe, ocean thermal energy conversions, and you can look at wave energy. I'm going to share here a link on the group. I believe CARICOM can disseminate to the to others also. Yes, so OTEC and wave energy, it's difficult to stand up on its own when compared to the other renewables based on not just overall power, but just the expenses and stuff at the same time. So it's more of a complementary. It can be used for more dispatchable power at the same time. So another research group I was working on, we just recently published this OTEC paper for the Caribbean here, looking at potential power outputs and stuff for different islands and scenarios. So you can have a check on that. It's open access that will help you if you're curious about those wave energies at that point. Yeah. So I'll
Thank you
that.
very
Thanks.
much, Dr. Kun. I see that Sherry-Ann is here.
Yes, Jordan, I just wanted to add also that as it relates to wave energy, David is correct that the pricing right now is not necessarily competitive when we look at the other renewables, but the Regional Universities Network is currently conducting studies and assessments on marine renewable energy in general. And looking for those opportunities across the region. So we're expecting that by next year, we would have had some pre-feasibility studies and maps completed that would help to better inform the possibilities for installing marine energy across the region.
Just one more second to say that, thanks, Sharian. Wind, offshore wind, is closer to grid parity than a number of the other marine options like tidal or wave or current. And also floating solar is a real opportunity for the region. So Sharian, look forward to those studies.
Thank you very much to everyone. I'm not seeing any more questions. So I'm just going to close off. It's been a very informative session on solar integration. And we'd like to thank everyone who attended, especially those who stayed past 12. Thank you to our presenters, Dr. Kun, Mr. Barrett, and Mr. Small for leading us through the content. And thank you to the SICRI team who continue to ensure the quality of our capacity building sessions. We'd love to hear from you guys, and we value your opinions, and we ask that you'd click the link in the chat and fill out the survey. And just in closing, I just ask you guys to remember the people of St. Vincent and the Grenadines and just keep them in your thoughts. And if you can, please do your part to help them recover from, the volcanic event. Have a productive rest of the day. Take care and goodbye. Oh, I'm sorry. Oops, there's one more question. How CREED can assist in setting up a solar system to generation power?
I think they mean SICRI, Jordan.
Yes.
Okay. Anyone here to answer that? Yeah, SICRI, sorry. So the SICRI has a project preparation facility which assists people interested in or entities interested in developing projects within the region. We provide technical assistance and financial matchmaking because sometimes projects will start but they can't find any donors or such, or they might be a good idea but they're not enough technical expertise to help them see completion. So you can visit the SICRI website, sicri.org/ppf, and you can read about the PPF. You can apply as well. And if you have any questions, you can email ppf@sicri.org. That's ppf@ccreee.org. All right. Thank you all for coming. It was a good session, and we'll see you at the next event.